Andre and I are back with another edition of the Qdrant 1.7 release. We're breaking down everything that came out in the latest release because there are some heavy hitters that have come out. So Andre, the CTO of Qdrant itself, decided to come on and chat with me to explain it all to me like I'm 5 because I am not able to wrap my head around it so easily. I'm going to get to ask him any questions that are needed. And I would love for you to also ask questions in the comments. We will get back to you on that. Today, in this video, we're going to be talking about sparse vectors. That is one of the 3 things, the 3 huge updates. The other 2, you can check out videos for those. One being custom sharding. This one that we're doing right now is the sparse vectors. And last but not least, we've got the discovery API. So, Andre, what are sparse vectors, man?
Hello, everyone. So, sparse vectors is something which was requested by the community a long time ago. And finally, we deliver this change. But I will start from the very beginning, because sparse vectors is a new concept for many of folks in the area, so it does require some explanation. So here on the slide, you can see the typical example of sparse vector. As you might notice, it now have 2 components, not just values, but also the second component, which is indices. And sparse vectors are an extension of just dense vectors, even though they operated the same on the mathematical level. So from math point of view, it's just the same vectors, but with a lot of empty or 0 elements. From storage point of view, it's completely different. From storage point of view, it now have first of all, unlimited size. So we do not even need to specify the size of sparse vector. It can have any length. And to efficiently store it, we actually preserve only non-zero elements. And as you can see here, we have a sparse vector example, which have 4 non-zero elements. And indexes of these elements are 102, 2000, 198, 92, and so on. All other values are zeroed out, and we don't need to consider them during the search. But I think the most important question here is how this sparse vectors actually obtained, and why are they useful for us if we already have a dense vectors. So let's take a look into this. Traditionally, the search was done with such algorithms like TF-IDF or PM25 or even bag of words, where you can split your text into tokens, then tokens converted into IDs based on some vocabulary, and then those IDs are assigned a weight based on the statistics of your dataset. In case of TF-IDF, it stands for term frequency inverse document frequency. So the more frequent the term is inside your document, the more valuable it is, or if it appears in a lot of different documents, then it's less important. And you can calculate the statistics to identify which words, which terms, which tokens are most important in your document. And in sparse vectors, you can naturally do the same thing. You can assign tokens with the weights based on statistics, and basically build the same search as you have in regular text search engines, but with this nice abstraction of sparse vectors. Essentially, it solves the problem of searching for rare terms. Like imagine you have a rare domain, like medical domain, or some custom documentation for some very rare tools or devices, where general purpose embedding models just cannot work efficiently. They cannot recognize words, and they just generate averaged vectors, which doesn't have any particular sense. In this case, searching for exact keyword is very important, and that's what regular text search engines were good at. But now with sparse vectors, we can implement the same technique, same approach of finding exact vectors, but with a nice abstraction of sparse vectors, which first doesn't depend directly on the statistics of the corpus anymore. You can assign weights to the tokens based on transformer models. There is a whole family of models which can generate and even expand your base vocabulary. It's called SPLET, and all of this can generate you the same abstraction we now support in Qdrant. So no need to decide upfront. You can give a shot to all of these approaches in your project and decide what works best for you. And Qdrant will work with all of them in just the same way as it works with vectors.
And so if I'm understanding this correctly, the end state here is things go faster, and especially things are more accurate also when it is these dense vectors that need more representation on what exactly it is, because it's maybe more of a niche thing and you can't quite get the best representation of what it is from a normal embedding model.
Yeah, in this particular domains with rare keywords, dense vectors doesn't work as good. They try to catch general meaning of the sentence, but it might not be enough. So in this case, you want exact keyword match, and the sparse vectors you can easily obtain this keyword match just because the specific components of the vectors are associated with specific tokens. But it is also extension of the traditional search, because now you are not relying on the statistics of the dataset. So even smaller dataset can benefit from advanced ranking, because we can apply transformer models to those tokens and not just BM25 statistics.
So that's how it helps with the keyword search.
Yeah.
Makes sense. Okay, so again, just to clarify that I understood everything, we can just start using this in Qdrant right away. Everything that you're talking about and these transformer models, we can test it out in Qdrant, see if it works for our use case.
Yeah. So Qdrant is agnostic to the choice of the model. We will work with any kind of sparse vectors you provide, and that would allow you to effectively and easily integrate this approach into your existing system. So you would not need to invent a new type of model which is compatible with Qdrant, because it's all just vectors. No need to change anything. And another important thing is that it actually allows you to combine benefits of both sparse and dense vectors in just a single request. That's basically what we mean by hybrid search. When we want to do search by both dense vectors and sparse vectors, get the result, and combine this result into a single list of outputs. In this case, you are no longer dependent on the legacy NLP stack, so you can forget about tokenization, you can forget about limitizers, you can forget about all this bulky pre-processing of your documents. It's all now handled by trained and efficient transformer models, so you don't need any of those. And at the same time, you do not lose any kind of precision when we are talking about the exact keyword search.
Okay. Now, you inevitably have seen on Twitter that there are people that are very opinionated about the BM25 way of doing things. And it feels like this is one different way of doing that. How can we compare the two? And I know you mentioned it in the last slide, like, okay, here's what it is. Can you give us a breakdown of BM25, the pros and cons there, and then the sparse vectors and pros and cons?
So BM25 is some concrete implementation of a concrete type of weighting tokens. So they already define how each term should be associated with which weight, and it's fixed. Everybody is doing the same thing in all text search engines out there. But sparse vectors doesn't limit you in the exact weighting strategy. So as a result, you can implement exact BM25 weighting inside sparse vector. So you will get exactly the same score, but with a technique which can later generalize to more efficient use case.
I see. So all that Twitter chatter is a little bit unwarranted, could we say? It's just for Twitter demos?
Yeah, sure. So in Twitter, I guess important part here is that Qdrant is still stays to be vector focused. We do not want to have any explicit text-oriented pipelines, just to not compromise our main original use case. We do implement additional features as soon as they benefit the main use case, which is a vector search. And the sparse vectors, I guess, is a great example of such vision, if you will. Because now we extend the ability of Qdrant to work with vectors. We cover new use cases. At the same time, we are still focused on vectors, and we do vector search as efficient as it possibly can be.
Okay, last question from my side is really digging into this slide about the hybrid search. And I'm wondering, so it feels like there's many different ways of doing this, and what you've seen work best / what ways are most recommended, or do you limit us in any way? Does Qdrant take opinions about how to do it?
Right. So Qdrant again does not limit you in any way in both pre-processing of sparse vectors. So whatever you can generate, whatever way you want to generate them, Qdrant will work with them. But it's also important that Qdrant doesn't force any post-processing and any kind of specific ways of how to combine results of dense vectors and sparse vectors. And I guess I have a dedicated slide even for this. So whenever you have a pair of result sets, you would need eventually to merge them into a single result. And there are a lot of research about it, how to do it properly. There are a lot of different approaches. Some approach are purely based on the scores of both results. So it's just operating with numbers. Other approaches try to utilize additional information from both documents and the query. Those models are usually called cross-encoders. So unlike vector and encoding models, they do not create this compressed representations. They just directly compare a pair of text. It is less performant. It requires more CPU resources because you need to compare each pair of results individually. But it also gives you better scoring result at the end, more accurate, more relevant data. Another approach can even use additional information on top of just text. So you can use personalization information, you can use some other sources of information enrichment. For example, if we're talking about e-commerce, you can say if this product is far away from user or not, it can give some ranking scores on top of just semantic similarity or text similarity.
Well, I think that's it from my side. Anything else you want to mention?
Well, yeah, we would love to see applications of this. We would love to see further development of tooling around it, because we see that it's even though we don't want to have any specific implementation of encoding and re-ranking inside Qdrant, we are completely open to implement those in side packages. And for example, we have this fast embed for dense encoding. We now can continue with this, improving this and introduce sparse vectors into it as well. It's all based on a community feedback. If there is a demand for sparse vectors, of course, we will do this.
Yeah. So if anyone wants to build on it, or if they want to talk to us on Twitter about how BM25 is much better, come at us. We're ready for it. And if you do end up building with it and potentially writing about your experience, let us know and we'll send you some shirts. That's all we've got for today. And thanks for watching.
Thank you.